Okay, so I realize that a lot of students have issues understanding the boundary conditions, and especially for beam and bending, when there are structures like these, when we have something extra apart from a determinate structure. For example, a cantilever beam should not have any support in the middle or on the right. So do you guys face this problem, writing boundary conditions? No? You're all good? Should I go ahead and try it out so that okay. So we'll take this problem where there is a cantilever beam and there is an additional roller support after a length of alpha L. Alpha is just a number which is less than 1, and this support restricts displacement. So we are only talking about planar problem. So we have a plane I1, I2, and we are considering transverse displacement in the two direction. So this roller prevents the movement along I2. So it doesn't allow any transverse direction, transverse displacement, whereas it allows a longitudinal displacement. So longitudinal displacement is allowed because it doesn't want any additional stresses for the beam and bending. For example, if I have a beam like this, and if I fix the displacement here and here, then if the beam bends, it would have additional stresses, actual stresses in the middle or anywhere in the interior of the beam. And the reason for that is that you are not allowing the actual displacement for it to compensate the length. So that's why the displacement is allowed in the longitudinal direction, but it has no implications whatsoever for bending. The only thing it does is prevent the vertical displacement u2 at that point alpha L, right? So so let's see what we can do for this problem. So we have a beam, and at alpha L there is a support. So we'll break this problem in two parts because there is a discontinuity at that location, and we cannot do the Taylor series expansion which we did for writing the governing differential equations, right? Do you understand when I say this? We cannot write Taylor series expansion. Okay. Then we have the first part of the problem. We'll take a small infinitesimal section here, and we have the later half of the problem. So this is where we have this support. Okay. So how many of you don't think that we need to write reaction forces here?
So you don't need to write like reaction forces because we're not like that. The reaction obviously comes out of the boundary condition. You know, like we're not writing a shear boundary condition at the end because there is shear, but we're gonna have shear like on the other end. So obviously you can find, you can like find it.
Right, right. So we do not write reaction forces here because the purpose is not to find moments in the middle of the beam, right? We write boundary conditions or reaction forces in when we are drawing the shear force diagrams or bending moment diagrams, because our goal is to identify that, and given loading could be in a particular region. For example, if I have a beam like this with a simply support, and my load is only applied here. When I'm writing the bending moment diagram, I take a section here and I consider everything on the left. Then this load doesn't show up in this area, right? But still there is a moment there. How do I evaluate it? I calculate the reaction forces here and then find out what's the moment. But we are not doing that here. We do not need to find moments. We are just writing everything in terms of displacements to solve it. Right, so we will write our governing differential equations in terms of displacement. We will write our boundary condition in terms of displacement, so that we have one variable to solve for. Okay, everybody on the same page? Perfect. So now I have the problem divided into two parts. So I need two differential equations, and if I have a problem which is well posed means has a unique solution, then I need to have four boundary conditions for each of these differential equations, right? So there should be two boundary conditions here, there should be two boundary conditions there, there should be two boundary conditions here and two boundary conditions here, right? But let's see what information I have and what can I get for this problem. Okay, so let's start with the first part. I have a differential equation which is H33 fourth times differential of U2 with respect to x1 equal to 0, because I don't have any distributed load in the beam. I just have only tip load. Okay, so this is my first equation, and H33 came out of these differential because we are assuming that it's a uniform beam. If it's not a beam of uniform material, we cannot assume that. It's a beam which is not tapered. If it's a tapered beam, we cannot assume this, that H33 can come out. The original equation is second order derivative with respect to x1 of H33, second order derivative with respect to x1 for U2 is equal to 0. So this is your original equation, whereas this is the moment. You differentiate it to get shear forces, and you differentiate it again to get the distributed load. So that's how it works, but we are assuming that it's made of uniform material, so H33 comes out and you get this equation. Now let's write the boundary conditions for this part. We definitely know that the displacement and slope are 0 on the left end because it's a cantilever beam, right? So I can say that my U2 at 0 is 0, and U2 at 0, U2 prime at 0 is 0, where U2 prime is essentially du2 over dx1. Okay, and I can now say something about this end of the part 2 because I know what are the boundary conditions there. So let me write part 2. Okay, and I'll say this is my part 1 and this is for part 2. So boundary conditions, I know that my shear force, okay, I know that my moment is 0 at the right end. So I'll say my moment at L for part 2 is equal to 0. But my boundary conditions need to be in the form of displacements because my variables are displacements only, right? So what I'll do, I'll just expand its formula. Okay, now I have a condition with respect to shear force because we have a point load there, so the point load will contribute to that shear force. So let's see what is happening at the right end. There is a shear force, there is a load P applied, okay, so I'll apply equilibrium there. We get V2 minus at L minus P is equal to 0. So we have H33 third order differential of U2 at L Oh yes, I think that's for moment. Let me see.
We have EV sur the x equals
I think moment is negative. Moment is negative of this, but because we have a 0 sign there, the negative sign went off. And then the shear force is negative of moment. So dm over dx1 is equal to minus v. So I think it's correct. Yeah. Okay. So we have boundary conditions at. Yeah. Go ahead.
So, like, instead of just saying V, like, what, you have like a V22 and a V21, what, you don't need V21 at all in that equation? If you do have it in that equation, is that fine or no?
So what's v21?
So, like, V21 is on that side, because, like, if you take the infinitesimal slice, you have, like, V21 down and then V2.
So I'm talking about this end right now.
Yeah, okay.
So that's why I have v22.
Okay.
So we have written boundary conditions of this end and this end.
Oh,
We still have to write something in the middle.
Oh, okay. I just assumed part 2 was the middle, but okay.
Right, right. So let's think about what's happening in the middle. We'll start with displacement. So any idea about the displacement? Yeah, go ahead.
I'm just explaining that the reason there's shear at the end of the beam is because the shear will be up and it's going to be canceled out by P, and then the sum then like is 0 at the end.
Yeah. So we are applying the equilibrium at the right end, and there should be some shear force V2, and P is applied. So we are just doing an equilibrium. If the P was not there, we'll say that shear force is 0. So that's standard we already know, right?
Okay. You it being on the other side. When you make like a slice on for the right part of the beam,
so you can do the same thing.
Yeah.
You have V here, you have P here. So it's essentially the same thing. You will do V2 minus P is equal to 0. So you get the same thing.
Okay.
Because this is positive downwards and this is positive upwards.
Cool.
Right. So both ways it works. Yeah, I don't want to mess up with your.
Yeah. No.
So yeah, I'll just erase this now. Okay, so we'll think about displacement. Yes, go ahead.
Sorry, but P is downwards.
P is downwards, so it was negative in the equilibrium equation. So P is like this, and my V is positive downwards. So my equilibrium equation is this positive sign because it's downward positive on the left side. Minus P is equal to 0.
Okay.
Equilibrium equation.
Wouldn't it be plus P if they're both in the same direction?
If the load was upwards, you would put it plus P.
You're saying the
Sorry, I didn't understand.
left side is down.
Yeah. So if you consider shear force on the left side of the slice, then this is positive downwards.
Right.
So positive downwards, positive sign, minus P, 0.
Because P is on the right side of the.
P is on the right side of the. You are doing equilibrium on the slice. Yeah, you are doing equilibrium on the entire slice now.
Right. Equilibrium, you're just looking at the direction of the arrow.
So
if they're both in the same direction, so they have the same sign.
So there are kind of two ways to solve this problem. Either you put equilibrium on the right side of the slice, for which V will be positive upwards, and you will do V minus P is equal to 0.
For instance, he did a similar problem, but he had the tip force pointing upward without the support in the alpha location, and he did the sum of the forces, and he had minus h33, the third derivative of displacement, equal P, and that was for P going upward.
Exactly. So this is P going downwards. So the P would have a negative sign. So I can look this up after class and see what the discrepancy is. So now at the middle section, at the section where we have an additional support, we look at displacement. So we can say that for the beam, which is part 1, the displacement on the right end of this beam is 0 because the support doesn't allow displacement, right? So we have u2 of part 1 at alpha L is equal to 0. Similarly for the left end of the part 2, so we have u2 of 2 at alpha L is equal to 0. Okay. Now what can we say about the slope? Does this pin joint restrict slope? No. So the pin joint doesn't restrict slope. So it has to be continuous. Yeah. So the slope on the right end of the part 1 should be equal to the slope of the left end of part 2. The slope should be continuous. The slope cannot be something that the beam deforms like this. There cannot be a sudden jump, right? So this is for displacement. So the first order derivative of displacement should be continuous so that it's smooth. And now what can we say about moments? Does pin joint restrict moments? There is no rotational spring. So there should be a moment continuity as well. Okay. So how many equations did I need? 4 and 4. So 8 equations. I have 2 here. I have third, fourth, fifth, sixth, seventh, and eighth. So this is a complete system. We do not need to go to shear force. Okay. And why is that? Because we are already defining displacement 0. So displacement 0 causes shear force to take a particular value, and that's the reaction force, right? So when you have a cause in the problem, you cannot have the effect on the same boundary. So if you are imposing conditions on displacement, you cannot have conditions on shear force. If you are imposing conditions on rotations, like the slope, then you cannot have a moment boundary condition. Because if you impose a condition on slope, means there will be a reaction moment, and that's unknown. We cannot say that moment will be of particular value or moment will be 0.
I'm sorry, but for instance, if we have instead of the support over there, an applied load in the middle of the beam, in that case we need to impose the continuity of the beam. So we will impose one on the displacement, but at the same time we will impose one on the shear force.
So on the shear force, you will now have boundary conditions. So exactly, you will get a continuity equation for the shear force if you have a load.
So this is what you're saying is valid only if we have support, right?
So this is a boundary condition, right? I'm saying that if you have a boundary condition, you cannot have a shear force boundary condition. But if you have a continuity of displacement, that's not a boundary condition. It's not saying that displacement is 0. You're not fixing any value. You're just saying it should be same. So you need one more equation in that time.
Okay.
Okay? So is that okay? So now because there is no distributed load, these equations are simple, and you can integrate them 4 times and then use these 8 boundary conditions to evaluate those constants. So this works because it's a simple problem and there are not too many complex boundary conditions involved. For example, these are 0, then moment is 0, this is simple value p, and these are continuous. So you can you can impose those boundary conditions, and that's what I've done. And that's what I've done here. I have found C1 0, C2 0, C1 plus some conditions with C2, C3, C4 0, and so I get 8 equations with 8 constants essentially, because when you integrate this equation you will have C1, C2, C3, C4 as integration constants. When you integrate this equation you will get say D1, D2, D3, D4. So you have 8 constants and you have 8 equations to get 8 linear equations, algebraic equations in C1, CIs and DIs, and you'll use that to solve for them. And finally you can evaluate the displacement. So this is for the first part, and similarly this is for the second part, and the total solution will be the displacement in the first part, which you get as an answer. You have to plot there with the domains of the first part, and then you will plot the displacement for the second part, which you get from these solutions when you are looking at that domain. Okay, that function for a particular displacement is valid on the domain of those displacements. And then I'm just plotting the displacement here. So if you move the support, if you see that, let's say the support is in the range of 0 to 0.5, there is hardly any so for example, if you have support here and if you have support at 0.5, the P causes some effect, but essentially your cantilever beam is being helped by putting that support. So when you're designing something like this and you want to restrict the displacement caused by P, you will think of a method like this and put a support in the middle, right? So by doing an analysis like this, you can see that if you put a support anywhere in this region, it's a significant reduction in displacement, right? By just putting a, let's say at 0.5, you can get significant amount of reduction in displacement, and then there is not much benefit. So all this analysis can be studied with any solver like Mathematica. But let's move on to another problem. Here we have a problem with 2 springs, and we'll quickly go over through the boundary conditions for this. So now I have a problem with two springs and a distributed load. For simplicity, the spring constants, both of them are same, and this is at alpha L, and this is also at alpha L. The total length of the beam is L. So we have a simply supported beam. So there is a pin joint or hinge at the left end, and there is a roller and a pin or a hinge at the right end, right? And we have 2 springs in the middle. So what do we know about this end? The displacement is 0 in transverse direction, and moment is 0, because this is a pin joint. It doesn't restrict any moment unless there is a rotational spring, but there is none. So there is displacement and moments are 0. The displacement and moments are 0 on this end as well, but the question is about what's happening at the center where there is a spring. So we can do again the same thing. We divide this beam in multiple parts, right? And we have to first think about displacement. So let's say this is my first part, this is my second part. I'll say my displacement at alpha L is equal to u2 alpha L for the second part. There is no support there, so I cannot say it's 0, but I can say it's continuous. The beam cannot fall apart. Then let's talk about slope. Should be continuous, right? There is no restriction on slope. So we don't have a boundary, but we have continuity. Then we talk about moments. So H33, well, not needed because it's same on both sides. So I'll just use U2 double prime no restriction on moments. I do not have a rotational spring, so should be continuous, right? So I don't have enough equations. I need 4 equations. I got that in the previous problem by saying my displacement is 0. So I had 2 equations here, but not in this problem. So we need one more equation on shear force. Right? So I have that thin slice where spring is attached, and I have a shear force on this end, and I have a shear force on this end. Let me call this say V star. And this is not a free body diagram, so let's make a free body diagram where this is a force applied. So considering that the displacement is positive upwards, so for a positive displacement upwards, the spring will exert a downward force, right? And similarly, it goes for the rotational springs. You have to look for the positive rotation and then oppose that positive rotation with a moment. So this force is going to be K U2 at alpha L. Okay, and I don't have a 1 or 2 there because they are the same at alpha L. So it's just KU2 alpha L, and it's applied in the downward direction. So I will do the equilibrium of forces there. So what do I have here? I have, let's say this is for my left end and this is for my right end. So VL at the left end minus KU2 alpha L because it goes downwards plus VR. Make sense? Equilibrium. And then I can say that I had other parts which are attached to this infinitesimal section, and the shear force is positive upwards here and is downwards there. So because of equilibrium, this shear force should be equal to this shear force, and this shear force should be equal to this shear force. So I can just replace those expressions there. H33 U2 triple prime for 1 at alpha L minus KU2 alpha L plus H33 U2 triple prime for the second part at alpha L is equal to 0. So that there you go. You have your 4th equation. You have 3 equations here and 2 equations on each end, right? So you have a complete system to solve. So this is a particularly hard equation to just solve everything by hand. I'm not sure, and you have a uniformly distributed load applied on the beam. So I'm not sure if you can do it by hand. You may be able to, but it would take you a fortune of time to solve it. So I just use a solver, put the equations, the variables, and get the displacements. And these are long expressions. Yeah, go ahead.
So, like, if you split it up into two sections, and then can you solve the boundary condition equations, assuming that like U2 starts at 0, and then when you put it into the final displacement equation, just do like x1 minus L over 2? Is that like, you know what I mean? Like, can you change the axis systems to solve, but then at the end transform, like to plot it, transform it back into?
If you are consistent such that you have not missed any information in the boundary conditions, I think you can do that.
Okay, thank you. Because it's really two separate equations, you know what I mean?
Yes, but they are
One
linked.
just starts after the other.
Yes, but they are linked here, right, at alpha L. So if you are particular about consistency, I think you will be able to get correct answers.
Okay, so you're fine with separating that into two, right? As long as they're consistent.
Yes, but how would you solve it if you separate them? I mean, if you bring the solution to me, I can tell you whether it's correct or not, and find errors potentially where you are going wrong. But if you can do it, there you go, another method. So we solve it here, and for example, if I can change the spring stiffness here and the locations. So let's fix this location at, say, alpha is 0.2, and now I'm changing the spring stiffness. So you see, after some point of spring stiffness, it just doesn't change the displacement. And if you go on increasing the spring stiffness, the plot will start by going downwards, and then it will pass through 0.2 where the spring was located. So what does it mean? It means that the spring has become so rigid that it's not allowing any displacement. So you can say that equivalently, it's a problem where you are restricting the displacement, right? If the spring stiffness is so high, then essentially you are restricting the displacement. You're not allowing it to move, and that's why you see that effect, right? But we did boundary conditions for two different cases separately. So how do we relate them? How do we say that this boundary condition is equivalent to writing U21 alpha L is 0 and U22 of alpha L is 0? How do we say that? So let's say when spring stiffness goes very high, so what happens to this equation? You take all these terms on the right hand side, divided by k, so essentially you receive that U2 alpha L is 0, right? Because the derivatives would always be very small already. So this equation would be equivalent to writing displacement 0 in that case. So that's why you see that after increasing the spring stiffness by a huge margin, you don't see any displacement. Okay, so this ends the examples. Now let's resume our regular topic. Which is on thin wall beams, and I understand it's pretty hard because thin wall beams are never easy to deal with, but we are aerospace engineers, everything is thin wall. So so the general assumptions that we discussed in the last class were the thickness essentially is much smaller than the cross-sectional dimensions, where you can define B and H as, for example, this is a thin walled section, then you can give this as B or this is H, something like that. When you have a Z section, for example, you define this as B and this as H. So there would be, even if the beam is thin walled, there will be two dimensions or multiple dimensions which you can associate. So any given cross-sectional dimension, the thickness should be very small for this assumption, right? So this leads to further assumptions such that sigma 1 is always significantly larger than sigma 2 and sigma 3, and then the shear stresses tau 1 2 and tau 1 3 are always larger than tau 2 3, right? So we assume that the stresses are only axial stresses because the beam is either in torsion or in bending. It can take up axial stresses, axial loads. So let us draw an arbitrary thin wall section, and we have the shear stresses which are in the coordinate frame I2, I3. So they are tau 1 2 and tau 1 3. So this is our curve C, and the coordinate is S that we defined in the last class. A curve, the center line is the C definition, and S coordinate goes along the curve C. So we can, instead of writing tau 1 2 and tau 1 3, we can define coordinates which are along this curve. So we can say that we have a shear stress which is normal, and we have a shear stress which is along the tangential direction, that's tau S. So tau S tangential to curve C, or is along S, whereas tau N is normal to curve C and is perpendicular to S. Okay, so now there is an angle alpha about which you are rotating the coordinate frame. So you can represent your tau n and tau s in terms of tau 1 2 and tau 1 3. So you can write tau n is equal to tau 1 2 cosine alpha plus tau 1 3 sine alpha, and you will write tau s as minus tau 1 2 sine alpha plus tau 1 3 cosine alpha. So the transformation of frames will lead you to two new vectors.
I have a question.
Yes.
Why? So tau 1 3 is along the I3 axis. Isn't that just sigma 3 or no? Like, why is tau 1 3 along the I3 axis and tau 1 2 along the I2 axis?
So these are the shear stresses,
Yeah.
and the way we define them is that they are normal to 1 and they are in the direction of 3.
Okay.
That's how the notation is.
Okay.
When we take an infinitesimal block in a 3D, we have shear stresses on the edges and the axial stresses, and then we do that equilibrium. So the directions are consistent from that.
Okay. It's your normal tool. Thank you.
Okay, so here when we define cosine alpha, it is essentially dx3 over ds, and similarly the sine alpha is minus dx2 over ds. So if I make a zoomed out version of this, you'll see that this is dx3 and this is minus dx2, and this angle is alpha because this angle is alpha. So this is 90 minus alpha, and you can calculate cosine alpha and sine alpha from there. Okay. So we have tau n is equal to tau 1 2 dx3 over ds minus tau 1 3 dx2 over ds. Then tangential shear stress will be tau 1 2 dx2 over ds plus tau 1 3 dx3 over ds. Okay, so let's look at this section again. We have a normal stress and we have a tangential stress, shear stress. So if this is my thin wall section, there is a normal shear stress in this direction. So if I have to satisfy the reciprocity of shear stress, there should be a shear stress in this direction as well to balance the shear stress. But this is a free edge. So in thin wall beams, tau n, which is the normal shear stress, goes to 0. Okay, so that it satisfies reciprocity. Okay. So given that T, the thickness, is very small, and tau n is almost close to 0 because of the reciprocity condition we have. So tau 1 2 is equal to tau n cosine alpha minus tau s sine alpha, and that will be equal to minus tau s sine alpha. So rearranging those equations, tau n goes to 0, you are left with this equation, and we have tau 1 3 is equal to tau n sine alpha plus tau s cosine alpha goes to tau s cosine alpha. So we have the values for cosine alpha and sine alpha, so we'll just say tau 1 2 is equal to minus tau s, actually plus, because sine alpha is negative of dx2 over ds, and tau 1 3 goes to tau s dx3 ds. So in our problem, tau s, if we take a cross section, cut it across the thickness, we'll see that tau s is fairly constant in the cross section because it doesn't get enough thickness to generate a variation. So the shear stress, which is tangential to that thickness, will always be constant or close to constant. So we can define some quantities, which is n of x comma s, x1 comma s, and that's sigma 1 x1 comma s times thickness, and I have f x1 comma s, and that's tau s times x1s times the thickness. So in thin wall beams, because the shear stress is generally constant along the thickness, a shear flow is being studied. The shear flow quantity is studied because the thickness is almost constant, so you just multiply the thickness with the shear stress and you get shear flow, and that's the quantity we study for thin wall beams for designing purposes or for calculating shear centers. And you must be familiar with this from your undergrad classes as well. So, and this N is actual stress flow. Okay, so in the next class we'll develop the equilibrium equations for this thin wall section, and we'll figure out how do we solve for shear flows and shear centers.